first speaker of the semester is Hannah. Hannah Arnold is a Ph.D. candidate at UNH in Ocean Engineering Department. She received her Bachelor's of Science in Mechanical Engineering in 2017 from the University of Miami. She's worked on combustion engineering for her undergraduate degree. After completing her undergrad, she's also worked as a software deployment system engineer at Raytheon Technologies in Massachusetts before returning back for a PhD. Aside from her PhD research, Hannah has also been a graduate advisor for the Marine and Naval Technological Advancements for Robotic Autonomy, MANTA RAY for short, group since 2020. And her PhD degree is currently being funded by the DoD Smart Scout program, and she will be working at Naval Undersea Warfare Center, Seaport, Washington, after she's done with her PhD. So, welcome, Hannah.
Good afternoon, everyone. Thank you for having me. This is also really special because I was one of the seminar coordinators for the 2024 to 2025 school year. So it's nice being back, even if it's on the other side. And I'm excited to talk to you all today about some graduate research going on in the MANTA RAY group. So we're going to talk a little bit about robotic fish, some artificial shark perception, and communicating with lights underwater. So let's go. So I'm going to start off by introducing the MANTA RAY group a little bit and what research we're doing. It's not just graduate research, but we have some undergraduate research going on. So I'll talk about that a little bit at a high level, and then I'll get right into the GOES Uncrewed Performance Platform Submersible, or GUPPS, which was Margaret Enderle's thesis research. Then go into the Marine and Naval Techniques for Integrated Sensing, or MANTIS, which is my perception research, and finish off with the underwater wireless optical communications research, which is being done by Jere in our lab group. So to start off, the Marine and Naval Technological Advancements for Robotic Autonomy group, or MANTA RAY, is a project here that started at the Naval Engineering Education Consortium effort, or NEEC, sponsored through Naval Undersea Warfare Center Keyport, and also now we have a NEEC project through Newark Newport as well. And over the years, so our project is also over a decade old, so we've been around for a while now. We've seen several major projects. We've had over 12.5 graduate students, and way over probably now 170 undergraduate students since we last accumulated these stats. And also to note, it's an interdisciplinary team. So we have students in ocean engineering, mechanical, electrical. We even have had marine biology students. So we're really getting an all hands effort on this research, which I will get a little bit further into on some later on slides. But MANTA RAY is also not the only group that Professor May Thane runs, which she also oversees the Advanced Controls Lab, or ACL, who we occasionally collaborate with, where MANTA RAY focuses on more of the marine robotics. So you have underwater robotics, surface robotics. The ACL then oversees your ground, air, space robotics. And Professor Thane's overall dream is to have friendly Skynet, which I always laugh about because Skynet's usually the bad guy, but we want it to be friendly. So we want this cohesive network of all of these different robotics throughout all of these different domains. And there's a lot of graduate students conducting research to accomplish all these goals through all of these domains. So for MANTA RAY alone, even just with our UUV research alone, you have my perception research going on, you have optical underwater communications going on with Derek's research, and also our master's student Seth. We have pitch control being looked into for the robotic fish by Maggie, or reinforcement learning research by Alex, one of our systems design PhDs. And for surface, so for autonomous surface vehicles, we've looked at model-based contingency motion planning, micro ASV hybrid control systems, and some AI-based systems identification, along with then going into the ACL, looking more into your path planning and controls research as well. And then for the vehicles for this research, which is where the undergrads come in because they are the ones developing these vehicles, really fine-tuning them over this whole decade-long program. We have this network of an autonomous surface vehicle, or ASV, which is the Orca in the middle, which is a pontoon-style ASV, which then handles all of the different uncrewed underwater vehicles, or UUVs, when they're in our fleet, which we have the Krill, which I won't unfortunately talk much about, I don't think, if any, in this presentation, but if you have questions, it's an experimental vehicle from Newark Keyport that can be tethered to the ASV. We have our Blue Robotics Blue ROVs, specifically heavy configurations, which can be run from the Orca ASV, along with our robotic fish, but we have this network of vehicles to then apply our research to, which in this case, and for this whole presentation, we're going to focus onto this perception research. So while my research is looking at developing the algorithms for perception, Maggie's GUPPS research was looking at a vehicle to deploy that perception, and Derek's communications research is looking to communicate that. So our general concept of operations here is to deploy all of these UUVs from some sort of central location like an ASV for local perception data collection, where these UUVs go out, get their detections, and then they're able to classify objects and localize their those detections with onboard GPS, and then eventually process this information in a way that once it's all communicated across vehicles, it's processed, and then they can use it to develop occupancy grids for mapping, for obstacle avoidance, digestion, and so on in the future. So that's just kind of your crash course on our graduate research in general. So I'm just going to now dive right into that research with GUPPS, which, like I said, this was Margaret, or we all call Margaret Maggie as well, and I think most of you in this room know Maggie, who finished her thesis at the end of last semester, which was MS in Ocean Engineering, where she was focusing on the pitch control for our GUPPS robot. So GUPPS itself is a robotic fish based off the steelhead trout. We chose steelheads to model it off of because of the Aquafort program here at UNH, where we have sustainable aquaculture research happening right off the coast of Newcastle. So what a good motivation to design this robotic fish on. And we've been printing it in-house using PETG and TPU filaments. So PETG is the majority of the fish, where the TPU is the caudal fin, or the end of the tail. So it's a little bit more flexible. It's using a multi-link single actuator propulsion method, and it has 1 degree of freedom, or 1 DOF, for its pectoral fins towards the front of the fish. And GUPPS will be used as a dynamic perception array. So we're looking at using several GUPPS in a multi-node configuration, with each having a perception sensor package on board. So that package would include perception sensors like your cameras and sonars, and then your ambient sensors as well, looking at data points like temperature and salinity. And it's meant to be unobtrusive. So we're modeling GUPPS after the steelhead trout, so it blends in better with its surrounding environment, using similar propulsion to the steelhead, so that subcarangiform propulsion with that small pitch angle behavior. And subcarangiform is a fun word to say, and that's really looking at the biological part of GUPPS. So that's where a lot of the biology research comes in, and subcarangiform is just the class of fish we're looking at. So that's including trout. And you can see, because of how the servo is configured within the body of GUPPS, so you have the servo itself is kind of mounted at the end of the body, and it's a rod-driven system where the rod is connected through this piece. We can get this kind of sinusoidal motion, which is mimicking the subcarangiform propulsion we'll see with the steelhead trouts. For the pectoral fin, pectoral fin started not very biomimetic, where it was based off of a NACA airfoil, which was very lovely for simulation modeling, since there is a lot of research on NACA airfoils. Fortunately, because of the size of the fin, even though it was similar to what you see ratio-wise in nature, it was not forcing the body of GUPPS down as much. So over time, the design became a lot larger, but also still became more biomimetic in a way where we were modeling closer to a fin that you would see on a fish in the wild, especially with the ray design on it. So it is just interesting to see how we go from a NACA airfoil all the way to this more biomimetic design at the end. And then all together with the pectoral fin inputs with how that tail is propelling GUPPS throughout the water, then we can look at how the pitch of the fish itself can be adjusted, which is what Maggie was looking at mainly, was that change in the angle of attack of the pectoral fins, or AOA, and how it would change that body pitch angle. Also for the heading of the fish, so the yaw could be adjusted by changing the axis of the caudal fin. So the line of travel for the fin itself is oscillatory, or it's oscillating, and it creates a net zero force propulsion. So the flick of the tail does one cycle, and that cancels out with forward movement. To change that yaw, you have to change the center of axis for the caudal fin, which is at omega. For this research, we were just looking at forward propulsion, but future studies could definitely look at then changing that yaw angle as well. For the actual guts of the fish, everything was packed in a Blue Robotics pressure vessel housing, where for the sensor systems on board, the inertial measurement unit being used was a Berry IMU 6 degree of freedom sensor, and then a dual pressure sensor configuration, which you can see in this image here, was also implemented by putting two Blue Robotics Bar 30 sensors, one on each side of the pressure vessel. The actual communications for GUPPS were handled using the Robot Operating System 2, or ROS2 communications, all handled on a Raspberry Pi Model 4B with the electronics diagram as you can see here. Communications itself were done via tether to a shore station, so a laptop on shore somewhere. So we were able to have user inputs go into GUPPS via guided user interface, or GUI, to real-time control the different angle adjustments for the pectoral fins, for the caudal fins, and so on. So for the modeling, a mathematical model based off the subcarangiform fish was put together by Maggie using these equations of motion here. All of this research can be seen in her publication for Oceans Halifax, which is this reference, or I can refer it to later if anyone's interested. But these equations were for the caudal fin propulsion, where these were for the pectoral fin, and she used MATLAB Simulink to model this all and get simulated results, which were also verified experimentally in the tank. These were the simulation versus experimental results for static pectoral fin testing, which was published in her IEEE Oceans Breast publication, where the fins for GUPPS were statically set at two different pitch angles, for here -30 and -45 degrees. And you're able to see how the angle of GUPPS, the body pitch angle of GUPPS, lines up pretty well with what was simulated using that Simulink model. And then also, Maggie was able to verify an open loop pitch control, also presented in that breast paper, where we got the simulation output and we're able to compare it across the actual experimental. And you can see these results were from this test here in the video, where GUPPS is descending, then ascending, and then descending again. And it's cool because you can actually see the fish kind of swimming through the water column. So I'll let you all watch this for a sec. The final study Maggie conducted was implementing a PID controller on board GUPPS. So she was able to simulate the controller itself and then experimentally validate again. These were the inputs that were used, along with the pectoral fins were limited between -45 to 45 degrees. This was the controller pectoral fin input with the response output as seen here. And again, we're able to validate those simulated results with the experimental, and the video for this trial here can be seen here. And to note also, these results don't look as clean as the last ones because of where GUPPS starts so close to the surface. The model itself was not accounting for those surface effects, which is what explains this noise that you can see here. And Maggie discusses that a little further in her thesis. So I can also refer anyone to that if they're interested. And similar here, just another trial showing kind of GUPPS working at the surface with the controller. But again, you see these effects in the results that were collected. This trial here, unfortunately, doesn't have video, but GUPPS actually was deployed about 0.5 meter under the surface. So these results you don't see as much of the surface effects from. And while this green line here is depth, so that matches this axis, the yellow line is the simulation results, whereas the blue and red scatters here are those IMU and pressure sensor outputs. So you can see when we're able to work around those surface effects, we can see it's better aligning with the actual simulation itself again. So to conclude this master's research on GUPPS and hopefully frame for future studies on the next slide, we've presented here this multi-link single actuator robotic fish with a flexible caudal fin with 1 degree of freedom pectoral fins for advanced maneuverability. You have your angle of attack adjustment through pitch and yaw. Maggie developed a 5 degree of freedom simulation model using Simulink. And verified that model using static and open loop control tests, and also implemented a closed loop PID controller for her pitch control. So moving forward with this project, because we really don't want to see this GUPPS research lost, and it's hopefully going to be implemented for some of my research. We'd like to expand the PID controller implementation heading. Add the actual perception sensor package, as this research has mostly been looking at that control aspect of GUPPS. It's really important for the perception research to really have an understanding of the orientation of GUPPS in the water. So that's why we've spent so much time on it, but it'd also be nice to start collecting some perception data using the fish, and then also create a school of GUPPS so we can have multiple to create that dynamic perception array. And then these were a lot of Maggie's references. So then going into now my research, which is the Marine and Naval Techniques for Integrating Sensing, or MANTIS. So why do we have these vehicles? One purpose is to collect perception data, as I've kind of said a lot so far. So I'm focusing on bio-inspired underwater perception. Using an n-dimensional approach, leveraging different sensor types. So I kind of mentioned it earlier in the GUPPS sensor package. So for that, we're talking about sonar and camera. For my research, even adding on other sensors like magnetics, and also leveraging those different viewpoints. And trying to generalize these techniques for modularity. So you can help with cost. So you're looking at putting this on different vehicle types. You're looking at using different sensor types, even different redundant sensor types. So using a low-cost sensor maybe in one package versus a high-cost sensor. And then also cut processing by having an understanding of how your sensors work in different environments. So you have all of these predetermined models that you can implement later on. Hopefully, with the end result, cutting processing time. And then I'm also using a model-based systems engineering approach to map out all these different algorithms and capture them accordingly. So exactly what is bioinspiration though? So with GUPPS, you were looking at biomimicry, where we were designing a robot around what you would see in nature. So for that case, the steelhead trout. I'm trying to do something similar as well with perception by taking what we see in nature with marine megafauna like sharks and dolphins. So with this image here, you can see the different processes a blacktip shark takes to get from detecting a prey fish to actually striking. So what sensor or what senses is the shark using? So the olfactory, visual, even the lateral line senses of pressure fluctuations and so on. How does it make those decisions based off what it senses to get from that detection all the way to the classification? And how can we actually implement that in a way artificially on board our different robotics? So to break this down, I've kind of isolated a couple of problem statements to really start diving into all of this. And the first one is, how do we actually understand those analog outputs from our perception sensors and how they're affected by the surrounding environment? So for the shark, if it's in a really turbid environment, maybe it knows it can't trust its eyes as well because there's a lot of sediment and everything through the water column. So maybe it will depend more on its acoustic senses or magnetic senses and so on. And then how can we leverage these performance models to unify the data together for that object detection classification? So how can we, when the shark's in that turbid environment, how does it also say, I can't really trust my eyes, but I see a blob there, and then I'm getting this sound and then this magnetic signal too. So how do I put this together and say, oh, I think that's an injured fish, I'm going to go after that. And finally, how can different vantage points be used to build confidence that the object being observed is actually correctly classified? So say you have a pod of dolphins and they're all working together to hunt something together. How do these dolphins communicate together to say, okay, this is what we're looking for? For today, I'm actually going to just focus on the first two pieces of this problem statement, but this third problem statement is actually what I'm working on for future studies with my research. So that first part of the first problem statement I presented, we're looking at our sensor performance model, and this is where my standardized heuristic algorithm for reinforced calculations, or SHARC, comes in, where I've developed this algorithm to capture modeling the ambient environment around the sensor and how the different sensors behave with it. And then incorporating this into a type 2 fuzzy logic algorithm, the weighted heuristic algorithm for localized entity evaluation. So for handling all of this information together. And then I'll actually present today an application to a real life scenario of swimmer search and rescue, which we presented at Ocean's Great Lakes last fall. So to dive right into things, for the sensor modeling, so an overview of SHARC, it's a 3-phase algorithm where you have to first identify the sensors you're using, so your ambient package and your perception package. So for the sonar, if we're modeling a sonar, we're looking at probably a CTD package for an ambient sensor. And then assessing the performance. So again, for that sonar, what are our predicted echo levels? And then also how can we use those to get our probabilities of detection? So using a mixture of simulation and experimentation to get that data, and then eventually apply. So when I modeled SHARC, it was in my publication for Oceans Halifax. We used a kind of range mission planning scenario where if you were out, or path planning scenario where if you were out, you can say, oh, my sonar is not going to behave in this water because of this environmental condition. So we're going to reduce our swaths so we can get more data because we can't trust the range. But then for Ocean's Great Lakes, we were looking more at implementing it into whale, which I applied to not only an acoustic sensor, but a thermal. So looking at that, for the Great Lakes paper, I was looking at a Blue Robotics Ping 1D sonar along with an MLX 9640 thermal camera. And we were able to model the performance data, so get those predicted outputs. So as I said, for the sonar, we're looking at the echo level. For the thermal camera, predicting what temperature would be radiated away from the camera. And then also using those to determine our probability of detection, which were then able to be input into our whale membership functions. I'm not including the models just for time's sake, but for the sonar, it was a mix of the sonar equation as well as using Michael B. Porter's bellhop simulation to model the transmission losses through the water column. And then the thermal camera, I was able to use some thermodynamic relations to assess the range. So if you're interested in those, we can talk about it later on. But getting right into the whale algorithm, which I said is a type 2 fuzzy logic algorithm, and how that works is you have these membership functions, which for type 2, you have these field of uncertainty bands. So that's actually taking those probability of detections, in this case, modeled from Shark, to determine those bands. So the more confidence you have or the higher probability of detection you have, the smaller those bands get because you're more confident in your results. But the less confident you are, the more that field of uncertainty will grow because you're just very uncertain on results. And then for the actual inputs, when you go down here, we're going to take those predicted values, so the predicted echo levels and temperatures, and compare them to the actual experimentally collected ones using a two-tailed z-score analysis to go into the inputs. Then these membership functions go through the actual fuzzy logic system where they're input into a linguistic rule set. This one here was actually based off of dolphins' echoic to visual perception. So the rule set itself is more biased towards the sonar, as dolphins tend to bias more towards their acoustic senses. And then it's output into a defuzzification function, which this one's actually based on Dalby et al.'s perform algorithm, where we can determine what confidence we kind of want to use as our classifier. So here we were using a value of 0.8 or higher. If we got a crisp output of that, then we said, okay, this is our swimmer in our environment. Then in my research, whale would be performed for every target within a frame of discernment. So one limitation of my research is that you have to assume every target is what you know. Every target you define are the only ones you know in your system. And that's just for sake of scope for my research itself. In the case of the swimmer search and rescue, we were just looking at the swimmer itself and a secondary target, which I'll get into later on. And that was our whole frame of discernment. But in future research, we're looking to expand that frame. And then for experimental validation, we used a micro uncrewed surface vehicle or micro USV right here in the Chase Ocean Engineering tank, outfitted with our perception sensors, so that sonar and thermal camera, paired with the complementary environmental sensors. And it was RC operated from a shore station, also using a ROS2 interface. And then the test itself was us driving the micro USV using a lawnmower pattern around random configurations of our targets, which our primary target here, the simulated swimmer, was a women's wetsuit filled with air-filled targets, with the head being a water polo ball with electronic hand warmers on it. And our secondary target here was just an air-filled drum, just to look for something else. And then the results from the z-score analysis, I'd also like to note the Blue Robotics sonar, we ended up finding some challenges. We weren't able to get the actual analog decibel values from that. It gives more of a digital output, and unfortunately there isn't a way to convert from those 0 to 255 values back to decibels. So for this study, I just use a yes or no if we detected. For future studies, we've already acquired a new transducer, so we will be able to get those actual Z-score comparisons, but for the thermal, we were able to get the comparisons between our predicted temperature and our measured, which you can see here. And then these, again, just to remind everyone, go right into our whale algorithm where the acoustic values go into our acoustic membership function, thermal goes into thermal, shark determines our fields of uncertainty, and then the rest of whale runs to get our crisp output, which we can see here. So for most of the trials, we were able to, well, for all of the trials, we were able to detect both of the targets. So that simulated swimmer along with our secondary target. For 5 of them, we were able to also classify our swimmer using that 0.8 crisp output threshold from our declassification. And you can see the barrel was also detected, but did not make that threshold. So we were able to say here that that was not our swimmer. Trial 5, while both targets were detected, there's too much sonar noise to actually detect it using the sonar. And because the rule set was so biased towards the sonar, even though we had adequate thermal results, we weren't able to get a detection. So that was kind of more of showing that's probably also what would happen in nature. If you weren't confident in one of your senses, then maybe you wouldn't get your full classification too. So just some conclusions for my research. I was able to show the developed local perception algorithm to utilize some predetermined sensor performance and also identified some sensor models used within the shark algorithm. I also was able to show you all a 2-sensor proof of concept to demonstrate the system. And for future work, I'm also working on incorporating additional sensors, really bringing this underwater. So it was easier to kind of do a proof of concept on the surface level, also just to get things going. But next stages would actually be taking things fully underwater, which means we won't also be using the thermal model anymore. We'll be shifting to more camera model. And also starting to combine local viewpoints, so taking different perspectives from either the same vehicle or different vehicles and getting that global perspective. And these are my references. Okay, now to end things off, I'll be going through some of Derek Perham's research. He's a PhD student in systems design, and he's been focusing on underwater wireless optical communications for underwater perception. So the purpose here is to really utilize the communication packet sizes to move perception information. And we're looking at optical also because it's a low cost version of communications. Acoustic comms can tend to be very expensive. So we're looking at alternative ways to really move this information, especially perception. You could be talking about large point clouds and so on. And so that could require a lot of bandwidth needed. And for the first stage of this research, looking at communicating all of the data to one central location. So kind of, as I said in the beginning, in our concept of operations, communicating everything to the ASV or somewhere else in the fleet. But eventually we want to decentralize these communications and have everyone in their own individual nodes. So each UUV can perceive their own environment in real time. And then that real-time perception can be used for UUV controls development. So this could be used to develop or populate occupancy grids, and then the UUVs can learn about the environment better in real time, and then know if there's an obstacle or something they're using those occupancy grids, and the cycle continues and so on. Past research, so a lot of this was based on a master's project by Igor Vladimirov in 2022, where he was looking to design a cost-efficient short-distance optical comm system capable of supporting this formation control over multiple UUVs. His research was considering the transmitter and receiver design, especially with the receiver design, looking at the different photodiodes to use for that. He also was looking into digital signal processing, specifically with the packet structures and the signal to noise and bit error rates. And then finally, he was able to test using simulation, and then also conducted some underwater testing right here in Chase where he was looking at different LED colors, the distances between the transmitters and receivers, and the different angles between the two, between the transmitters and receivers as well for the optimal range, with those ranges looking between 15 and 20 meters. Again, clear water since it was just right here in the tank. And then he also was able to do some in-air communications testing for different nodes to mimic that multi-UUV communication, where he was looking at, I think he got about 5 kilobits per second for his air testing. The current objectives then is to improve upon this research for that multi-UUV communication, so increasing that speed, reliability, and so on. So to do this, Derek and other students in the lab have been evaluating different hardware methods for optical communications, and then looking to apply this to multiple UUVs within the formation, and then bridge that gap between communications and UUV controls, again, looking at the centralized versus decentralized and so on. Also, this research is looking at the diffused line of sight method. So we're using LEDs in the lab versus point to point, which you could use a laser for. The bias is towards diffuse because while that point to point can have higher data rates, it requires much more precise pointing, so much more refined controls. So just to generalize the scope to start, they're looking at diffused line of sight. This is currently the proposed signal algorithm that Derek's been studying, which he's also implementing using simulation within MATLAB, Simulink, and Simscape to simulate a real-world physical system using a physics-driven approach. And then for his actual signal modulation, and this is where things really start differing from Igor's research, is he's looking into using a quaternary frequency shift keying approach, where you have patterns of 2-bit symbols tied to increased frequencies to allow for more perceived data throughput, where the actual data throughput remains the same. And an example of this can be seen here. So this is what he's actually simulating using the Simscape environment. And then he's able to model the transmitter, which was designed using, considering the QFSK method, where the LED is a light source to transmit the signal. A Raspberry Pi is controlling the pins of the transmitter to flash a light, and a MOSFET is used to connect the LED to the power source. So this is based off of what Igor did and the actual hardware implementation of his master's research, and moving that forward into simulation and eventually another hardware implementation. And the receiver is a little more complex than the transmitter, where a filter is involved, where that light source will go through a filter that has a readable window that's centered on transmitting the wavelength. And then that light will then be captured by a photodiode to read the signal, and then the signal itself will be filtered and amplified to a readable output. And this research is a little earlier on, so there isn't as much, but moving forward, there's a continuation of that simulation work to really capture results. And then actually the implementing the physical experimentation of the receiver and transmitter using that multi-UUV configuration, taking Igor's work from air and putting it underwater. And then the implementation of the controls using the underwater optical comms, and then the demonstration of the communication of the perception package to then be used for the occupancy grid development. And these are Eric's references. So that's all I got for you guys today. And I'd really like to acknowledge the University of New Hampshire. This project couldn't be done without the university. We've had a lot of support from various ocean engineering faculty and staff throughout the years, and especially the MANTA RAY research group as well, past and present. This is actually our group of students from last summer, so a mix of undergraduate and graduate students, as well as our fellow ocean engineering grads. This research is also not only being funded through the NEAC vehicle, but also through the Office of Naval Research, through the Naval Undersea Research Program. A lot of my research is funded through that. And our partner for that is also Newark Keyport. And I'd also like to acknowledge Naval Undersea Warfare Center in Newport, as we have a neat grant with them now. And as Ishan said at the beginning, my research is also being funded through the DoD Smart Scholarship Program. So I'd like to give them a shout out. And I'd like to open up for any questions.
Is there a specific reason that the GUPPS is doing the biomimicry? Is it so it doesn't? Is there a specific application that requires it to blend with the environment?
So when we first designed GUPPS, it was around using it in conjunction with the Aquaphor program. So as a way to incorporate a robotic fish that looks like the steelheads that are being farmed out there in a way that may not alarm the steelheads or just have them integrate into the environment around them. One of our biology student projects that we had on Manta Ray a few years ago actually found that the farmed steelheads don't really care about what's in the pen with them anyway. So we've been trying to figure out different applications now for GUPPS, but that was kind of why we modeled it after a steelhead to begin with. And it may be better to model it after maybe a different subcarangiform species that might be more affected by foreign robotics in its surroundings. Like the steelheads, they're used to boats coming and going multiple times a day and divers, and so they're really used to human intervention. Whereas fish in nature, who might not have that intervention as much, might be more affected by a random robot fish that comes in or something. So,
But yeah, there hasn't been like a specific test yet with wild fish or wild.
not with wild fish.
Okay. Thank you.
In the future measurements, did you say for your specific research that you'd use underwater thermal cameras?
Yeah, so one of the sensors I'm looking into now is actually using Raspberry Pi cameras, and I'm looking at how color changes as a classifier for one of my components for the models, and then using cameras. Mostly because, as I kind of alluded to, thermal doesn't work underwater. So while it was great for my proof of concept, I'm not going to be able to actually apply it on the underwater vehicles portion. So I'm looking at using a different optical sensor and then developing a new model around that and so on to do that. Also, as a radiative sensor, I'm also looking into magnetics. So that is kind of similar with the radiative decay that you see with the thermal. So we're looking to see how the magnets can be used to classify objects.
Thank you.
Yeah.
Kimmel Online says, for the shark work, it struck me that the problem statement did not relate specifically to fish/sharks. Were you able to borrow approaches and experience to perception from other creatures, aquatic or otherwise?
So that's kind of where the whale development is going to come in. So that linguistic rule set is where I'm taking observations of perception from the marine megafauna. So for my swimmer proof of concept, I was just looking at dolphins because they had those two senses. But moving forward, I'm going to look more into how sharks perceive the environment around it. And actually, that image that I had on the bio inspiration slide, which I can go back, that was from a biology paper of how sharks from different ecological niches in sensory deprivation react to things. So this figure right here, so I'm going to try to take that sensory deprivation information to then build my next linguistic rule set, especially as I'm incorporating more and more senses into the whale approach. So that's kind of where I'm starting to lean more into the biology side of things.
In general, John, I assume related to you based on the last name, says PID adjustments, AOA, underwater drone, love it. As an experienced open water scuba diver, definitely appreciates the whale for locating people in open water.
Exactly.
So with the kind of the future, but using a bunch of different sensors, do you have to worry about the field of view? Something like that, a smaller cone than something like a 360 degree.
Yeah, so that's gonna have to be a consideration, especially when we start taking in the different viewpoints, because if you're looking at it from, say, in the optics community, like mosaicing, where you take those different viewpoints, you're gonna have to make sure that whatever you're actually sensing is the same across that. So that's going to really start mattering when we're looking at that information there. So having that spatial view is going to be necessary.
On the great job, by the way. For GUPPS, how was the biomimetic fin designed? I assume like in a 3D modeling software, but what was kind of the dimensions about it? What's the kind of work to make it look like?
I'm honestly not sure the exact steps we took to get from that NACA airfoil to the fin itself. I know we had some help from past biology students on the team as well. Maggie might have a better answer for you if you want to reach out to her.
Can I step in on that? It was fundamentally developed by a marine biologist and undergraduate, and we tested some of that, and mechanically it just was not efficient, and so we efficientized. So it was a evolution of things. But that's a fair question.
No further questions, then